In this next series of videos, we're going to be focusing on the reaction rate and substitution regioselectivity of electrophilic aromatic substitution. To begin this discussion, to begin this lecture, I want to look back at the energy diagram of electrophilic aromatic substitution, right? And so what we're looking at here on this piece of paper is we have just the generic mechanism for electrophilic aromatic substitution, starting with benzene. Pi electrons break, make a bond to the electrophile, and then some base comes along, plucks off a proton, and we re-aromatize. So we're doing the substitution, substituting a hydrogen for an electrophile. Remember, this is a two-step mechanism, right? So step one, step two, right? Reflected onto the energy diagram, going from benzene to the rhenium ion, and then down to the substituted benzene. Right, so on the energy diagram, this would be step one, and this would be step two, right? It's important to note that step one is the rate limiting step, right? So the formation of that intermediate, of the rhenium ion, determines the rate of the reaction, right? How fast that reaction occurs, or how frequently that occurs over time. Right, so it's important to note that anything that we can do to stabilize the rhenium intermediate, to lower the energy of the rhenium intermediate, is going to lower the energy of that first step. Right, so the question that we're asking today is, what is a substituent on that benzene ring going to, how is that substituent going to affect the energy of the rhenium ion intermediate, right? So if we put an R group here, and the way that I'm drawing this R group, you can see that it's not attached to any one carbon. And this is a way of just saying there's an R group somewhere around this benzene ring, all right? But we're not saying where it is, right? There's an R group attached. So we'll put an R group there, carry that through. Okay, so the question that we're asking is, how is that R group going to affect the energy of the rhenium intermediate, right? And all of the discussion that we're going to have today is going to be centered around, or the assessment of, the rhenium intermediate. All right, so anything that we can do to lower the energy of that rhenium intermediate, right? So if we make that rhenium intermediate lower in energy, right, then the transition state that leads to that rhenium intermediate is also going to be lower in energy. All right, and so what that means is that this is going to correspond to a faster reaction rate. Okay, so R groups that stabilize that rhenium intermediate are going to, or benzene rings with R groups that stabilize that rhenium intermediate are going to undergo substitution faster. Likewise, R groups that make that rhenium intermediate less stable, right, that positive charge higher in energy, are going to have a higher energy intermediate, or form a higher energy intermediate, right? And the pathway that leads there is going to be a higher energy pathway, and is going to correspond to a slower reaction rate. Right, so if we have, let's see if I can, if we have an R group, if we're forming a positively charged intermediate, and we have an R group that makes that positive charge even more positive, right, and that's going to form a less stable intermediate, and therefore be formed through a slower reaction. Okay, so what we're going to do is look at the types of R groups that we can have on a benzene ring, and we're basically going to divide those R groups into two different categories. Okay, first category are going to be R groups that we categorize as electron donating groups. Or what we'll abbreviate as EDGs. All right, so electron donating groups, let me draw some out here. They're typically going to be groups that can push electrons into the ring either through resonance or through induction. So some common ones would be a benzene ring with an oxygen attached to it, right? Or a benzene ring with a nitrogen attached to it, right? So maybe you could start seeing a pattern here, right? So we can also think about having a benzene ring with a thiol group, right? Or a benzene ring with a phosphorus atom attached to it. All right, so you can see all of these are going to have either one or two pairs of electrons, right? And those electrons can be donated into the benzene ring, right, and participate in resonance, right? So those electrons are in conjugation with the benzene pi system. Okay, likewise, some other electron donating groups, or groups that we consider electron donating, right, would be an alkyl group, so methyl, ethyl, isopropyl, okay? And another class, which we probably won't see very often, but is important to note, are silyl groups, SIR3. Okay, these, unlike this group up here, these electron donating groups do not have lone pairs on them that can be donated into the ring, right? So these are not resonance donating groups, but these are either inductive or hyperconjugation donating groups, right? So alkyl groups and silyl groups, right? The bonds to hydrogens and other carbons beyond this first carbon can overlap with the pi system and stabilize positive charges within that pi system through hyperconjugation, right? Both alkyl and silyl. In addition, the polarity of the silicon-carbon bond is the electron density sits more on carbon. And that is also, if you're forming a positively charged iridium intermediate, that polarity, the polarity of that bond is going to help stabilize that iridium intermediate a little bit. All right, the other category of groups, rather than electron donating groups, we're going to look at electron withdrawing groups. Or EWG. Right, and electron withdrawing groups are going to obviously be the opposite of electron donating groups, where electron donating groups are putting electron density into the ring. Electron withdrawing groups are going to be removing electron density from the ring. So common electron withdrawing groups, and I'll draw these in red, are carbonyl groups, ketones, aldehydes, esters, amides, right? Things where you have a single bond and then a double bond to oxygen. The nitro group is electron withdrawing. Strongly electron withdrawing. Let's see, the sulfonate group. Right, so we're learning how to make sulfonic acids in this chapter. Those are electron withdrawing. And then we can also look at cyano groups or aryl nitriles as electron withdrawing groups. Okay, and so these are all resonance electron withdrawing groups, right? So that we can, they all have a double bond that's in conjugation with the pi system, right? So we can remove electron density, push it up towards the more electronegative atoms, the oxygen atoms, right? Or in this case, nitrogen, right? So that shows how resonance electron withdrawal can occur with these groups. All right, we also have other electron withdrawing groups that don't have resonance. One example of that would be trialkyl aryl ammonium compounds. So NR3, and then there's a positive charge on nitrogen. Right. We also have trifluoromethyl groups or fluoroalkyl groups, CF3. All right, and so these withdraw electron density because the polarity of these bonds, or the polarity of those groups, is going to be pulling electron density out of the ring, right? So nitrogen with a positive charge is pulling on all of those bonds attached to it to get those electrons back, to get a pair of electrons back to become neutral, right? So that's going to withdraw electron density from the ring. Then here we have the inductive effect where the three fluorine atoms are pulling electron density from carbon, and carbon is going to be then therefore pulling electron density from the ring to make up that deficit, right? In addition, the nitro group also has inductive electron withdrawal, including the resonance electron withdrawal. Okay, so when we think about how these different groups are going to affect the rate of a reaction, okay, if we have an electron donating group on a ring, generally those electrophilic aromatic substitution reactions will occur faster because that electron donating group can stabilize the rhenium intermediate that forms, right? So here we would draw EDG. Oop, this is the rhenium intermediate, so there's no bond there, so erase that. Okay, so if we have an electron donating group on the ring, that rhenium intermediate should be stabilized because that electron donating group can put electrons into something that is positively charged. All right? Likewise, electron withdrawing groups are going to make substitution more difficult, right? Because they're going to, if we have a group that's withdrawing electron density from a ring, you would imagine it's going to be harder to form something that's positively charged from a ring that's already electron poor. Okay, and so we see that as a higher energy rhenium intermediate that's going to be formed through a higher energy transition state and therefore correspond to a much slower reaction. Right, so we can further categorize or qualify electron donating and electron withdrawing groups. So we would qualify electron donating groups as being activating groups. Meaning that they speed up that electrophilic aromatic substitution, right, by decreasing the intermediate energy, the rhenium intermediate energy. Okay, so decreases the intermediate energy and increases substitution rate. Okay, and then we can further qualify electron withdrawing groups as deactivating groups. All right, and deactivating groups will increase the intermediate energy. All right, and therefore they will decrease the substitution rate. Okay, so just to look back at our energy diagram, this black pathway, that's the substitution, that illustrates the substitution pathway of benzene. Okay, so relative to benzene, if we put an R group onto a benzene ring that is electron donating, those reactions should occur faster than benzene, than the substitution of benzene. Right. Furthermore, if we put an R group on a benzene ring that is electron withdrawing, that we can qualify as electron withdrawing, right, those reactions will occur more slowly relative to benzene. Right. So as you can see, the type of substituent, well, substitution overall will affect the rate of electrophilic aromatic substitution, but we have to consider the type of substitution or the type of substituent before we decide how that reaction rate will be affected. In the next video, we're going to look more closely at how these substituents affect the substitution regioselectivity of electrophilic aromatic substitution.